Okay, I think I'm ready. Advent of Code 2025, Day 10 is called Factory. Just across the hall, you find a large factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline, and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. That's a kind of dog, right? Japanese dog. All that remains of the manual are some indicator light diagrams, button wiring schematics, and joltage requirements for each machine. For example, I can see today is going to be a parsing day. What does all this mean? The manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics in parentheses, and a joltage requirements in curly braces. To start a machine, its indicated lights must match those shown in the diagram where dot means off and hash means on. The machine has the number of indicator lights shown, but its indicator lights are all initially off. The machine has a number of indicator lights shown. Smab says, I wish it was a parsing. Okay. So an indicator light diagram like dot hash hash dot means that the machine has 4 indicator lights. Oh, okay. So it's saying that, so this one has 6, and this one has 5, this one has 4. I understand. Parsing I can do. Okay. Well, we'll see how far we get with this. Everybody said 9's part 2 was painful, and it took me a while to figure out how to solve it, but I got there. I got there in the end. So an indicator light diagram like dot hash hash dot means that the machine has 4 indicator lights which are initially off, and that the goal is to simultaneously configure the first light to be off, second light to be on, third light to be on, and the fourth light to be off. You can toggle the state of indicator lights by pushing any of the listed buttons. Each button lists which indicator lights it toggles, where 0 means the first, 1 means the second, and so on. So the buttons are in the parentheses. I see. So 0 means toggle the first light. Is it left to right or right to left on the lights? Because unfortunately, the example here is same both ways. It's a palindrite. Map says, I think today's in your wheelhouse. I got there in the end. Okay, good. When you push a button, each listed indicator light either turns on if it was off or it turns off if it was on. Okay, so we're toggling them. I see. You have to push each button an integer number of times. There's no such thing as a half a press, nor can you push a button negative number of times. Okay. I wonder how that would come into play. So a button wiring schematic like 034 means that each time you push that button, the first, fourth, and fifth indicator lights would all toggle between on and off. If the lights were hash dot 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 dot, pushing the button would change into be dot 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 hash hash dot instead. Okay, so it's leftmost is 0 and rightmost is the MSB. I got it. Because none of the machines are running, the joltage requirements are irrelevant and can be safely ignored. I guess they're part of part 2. You can push each button as many times as you like. However, to save on time, you will need to determine the fewest total presses required. Okay. I think I understand the puzzle. Let's parse it out, and while I think about my approach. So we're going to have a machine which is going to be looking for a desired pattern, which is going to be, let's create a light struct. We're going to have buttons, which is going to have a vec of button. Sure. And then we'll have joltage, which we're not going to use yet. So I'll put an underscore there for now. And it's just, for now, I'll just make it a vec view size and we can worry about it later. I mean, the other option is just leave it off and forget about it for part 1, and then we'll add it in for part 2. Maybe that makes the most sense. It means we'll have to change the parser for part 2, but we might have to anyway, because maybe a vec view size is not the right approach for that. So I'll just leave it out for now. Let's do lights, struct lights. Let's get my input here. and take a look. The reason I was pausing is because what I was thinking of doing is just using an unsigned integer of some size, but it all depends on how big these things can be. Because if they get bigger than like 64, then I'll have to use a U128. Let's find out. Awk. How many people here use awk? Print, length, $1, less than input 2025-10, sort-n, tail-1. 12. Okay, so they get as big as 10 bits. Right, I'm subtracting off the square brackets from the length, and so they can get as big as 10. So that's reasonable. We can just store that in a byte, actually. Oh no, 10. What am I thinking? Let's just store it in U size and just be done with it. Not use awk in 20 plus years. I use it every day. Well, almost every day. And then we have buttons, and buttons are going to be I guess the same thing. We'll just use them differently. You can apply buttons to lights, but you can't apply lights to buttons, for example. Right? Because if what we can do is impl a push on lights that pushes the button and it toggles all the bits. And since it's just toggling, it's just an exclusive OR application. So let's figure out how to parse these things. And we're going to call it machines. It's going to be a vector machine. And so this is machines. Let's delete that, pull it in where it belongs, and then we'll see, you know what I'll do is I'll move these up here so we can impl on machine from stir. Impl from stir for machine. Infallible. Okay. So first thing we'll do is we'll split by white space and collect that into a vec. Let entries equals s.split white space collect vec. Okay, and now we know the entry of 0 is going to be our lights pattern, and entries 1 through n-1 are going to be the buttons. And we'll just ignore the last thing for now until we get to part 2. I assume this can be used in part 2, otherwise why have it there? So we can actually do the same thing. We can impl from stir for lights. And this is going to be, so the first, what we can do is walk the chars and toggle the button. Right. And so the reason I was pausing is because I was thinking, well, we should just grab 1.n-1 to ignore the brackets, but we can ignore the brackets anyway by just looking for a hash. Oops, I meant to click here. So maybe that's too clever, but we can say, okay, well, let's do it iteratively, and then we can make it functional if we need to. Lights is equal to 0 for IDX CH in S chars enumerate. If CH is equal to hash, then lights or equals 1 raised by, or 2 to the IDX minus 1. And this should be safe to subtract 1 because we should never get a hash sign on the 0th entry. And then we can just say, okay, lights. And that gives us that. We'll do the same thing for button, or something similar for button, from stir for button. I don't know why I'm doing it by hand. Let's not do it by hand. It takes longer. Infallible. And now each button is going to be surrounded by these. So maybe here we do handle it this way. So we can say let nums is equal to s of 1 dot dot s dot len minus 1 split on comma map num parse unwrap collect. Actually, I could just shove it directly into OK button. I should be able to do that. Consider specifying a generic argument. Oh. Sorry, I was collecting all of these as individual what's it is. Maybe we just do that. Back usize. Should know, right? Oh, that's why I didn't need to. Okay, let's try that. That's on the map. That collects. That gets the button. That's the OK. Oh, I see. I got too many things here. There we go. Okay. So the entries, so we can say let lights equals entries of 0 dot parse unwrap. Let buttons is equal to entries of 1 dot dot entries len minus 1 map e parse unwrap collect. And then this is OK self lights and buttons. Oh, it's called pattern. I call it pattern. This is the pattern we're trying to match. It doesn't like that. Entries is a vec of stir. Oh, I need to iter. All right, so we have machines. Let's grab the test input and see if we can print the machines out and see if it parses it correctly. So I can just say println dot this machines. Oop, that's it. That's the whole thing. I meant to do just a test. So we can take a look at we can compare. Whoa, I did not mean to do that. Okay, so the lights are going to be 1, 2, right? So this is 1, 2, and 4. So the pattern should be 6. Yes. Here the pattern should be 8. Yes. And here the pattern should be 16, 32 plus 8, which is 40, 44, 46. Yes. Okay, that worked. And we have a button of 3, of 1, 3, of 2, of 2, 3, all the way down to here where we have a button of 1, 2. And we're ignoring the joltages for now. Very good. Okay, so we're parsing it correctly. Part 1. So I've been thinking while I was doing this. There's a couple of approaches we could use. One, we could just try every combination of button. I don't know if that would be sufficient, though. There might be, pushing a button twice does nothing, right? Because it toggles all the bits once, toggles all the bits another time. So we could, given that there's only 10, so there's 2 to the 10, or about 1,000 different options per machine, we could just do all the combinations, right? And then the first one we hit that has the lowest number of button pushed. But I think it might be cleaner to just use BFS. Impl machine. Append find pattern self. That might be the easiest way to do it because I already wrote BFS. AOC lib BFS. It's just this code. So it needs a starting location, which is a reference to a state. It has a neighbors function, which given a state returns a vector of new states. And then we have to see if we give it a function that tells us whether or not we hit the endpoint. I think that might be all we need to do. So our starting location is, or starting state rather, is a reference to, I'm going to say 0 for 0 button pushes. And then it said all the lights start out off, correct? Yeah, its indicator lights are all initially off. So that's the equivalent of lights 0. Okay, so the next thing is the neighbors. So we have a state, which is broken down into a count and a lights value. And then we have finally an end state, which is going to be a count and lights as well. And it's going to say if just basically lights is equal to self pattern, which means we need to add EQ and partial EQ onto lights. Right, and this is just going to say, for now, I'm just going to say vec new. Just to get it to compile, just to make sure I have everything correct. I don't know if it's going to be an infinite loop, so I'm going to quit out of this. It shouldn't be, right? It should return nothing. Oh, this needs to return the count, usize. And AOC lib BFS returns what? A vec? No, it just returns an option of S. Oh, right. S is just the count. Okay. So I can say I can just do this, right? And it should assume that that's correct. Am I a Rust enjoyer? I am. Unwrap. Okay. Treatbound lights hash is not satisfied, right? And lights clone is not satisfied. Okay. Let's just do copy and clone while we're at it. And consider dereferencing this guy here. All right, so we got it to compile. It shouldn't give us an answer. Well, I'm not even calling it yet. Method find pattern is never used. Okay, so let's write part 1. Part 1 is going to be self machines iter map machine find pattern, I think is what I called it. And then we're going to just sum those up. Right? And now it's being called, but buttons are not being used. Yeah, because we're going to use buttons here in the function. So cargo run. Yep, option unwrap on none value. Okay, very good. Let's get rid of that print statement. Okay, so I think I can do this now. All right, so the next thing to do is to actually write this neighbors function, which I think is going to be straightforward. All we need to do is return all of the values after applying the buttons to the lights. We don't need this count. Let's just underscore that. So we just need to loop over all of the buttons for B in self buttons. So for each button, we want to apply the light to it. So actually we should be able to do this, right? Self buttons iter map B let's say lights.apply B or push. Let's say lights push B and then collect. Right, we're just pushing the buttons on the lights. And right now we don't have that type. Oh, I forgot to put a comma there. Okay, so now we need to push button, generate push method. And here it is. What's this I32? Why does it assume it's returning an I30? Oh, right, I need to return a count plus 1. So we actually need to map it differently here. We need to map it as count plus 1 comma, like that. This should be a usize and a lights. And now we're getting a type mismatch in the closer because I forgot this. Fair enough. Why does it think it's... This is a reference to a usize. That's a usize. Do I have to do this? What is it telling me? Okay, let's go back to BFS and see what it's assuming. It's assuming a vec of T. Oh, okay. So if it's assuming a vec of T, we don't actually have to put this count plus 1 business here. I'm curious, why did you choose BFS? Why not? Why did I choose BFS? I thought it was the most straightforward thing I could think of. Lights.push. Why did it assume it's going to do this? We're going to just return lights here. This is the bug. And now we can't collect. Value of type vec usize lights can't be built from that. Okay, let's try again. Do I really need to say count? I do need to say count plus 1 because we need type T there. There we go. Okay. Yeah, I mean, the other option, McNets, the other option I was thinking of was just looping over every possible combination of pushing the buttons. Because you only ever have to push the button once. You never have to push the same button more than once because they're toggles. So pushing the same button an even number of times is like pushing it 0 times. So, but I thought BFS would be fun. And less annoying than figuring out how many times I pushed a button. So now we have to implement push, which is going to be for, let's call this button. For B in button. Oh, we're going to create a new lights. Let lights is equal to self 0. Lights exclusive or equals. Does Rust do that? 1 shifted by B. And then this would be lights. Button is not an iterator. I thought it was button.0. There, 7. Is that correct? It's 7. Look at that. Okay. Sorry, readjusting my mouse here. All right, let's try with the real input. 466. 466, return. Hey, that's the right answer. Clippy likes everything. Beautiful. If Clippy likes it, that means it's good code. Yeah, I mean, this seems straightforward. So part ones generally are. Git commit -am AOC 2025 day 10 part 1. Oops. AOC, yeah, AOC 25 10. All right, let's see what part 2 is. All of the machines are starting to come online. Now it's time to worry about the joltage requirements. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the voltage levels. Ignore the indicator light diagrams. All right. The machines each have a set of numeric counters tracking its voltage levels, 1 counter per voltage requirement. The counters are all initially set to 0. So voltage requirements like 3547 means that the machine has 4 counters which are initially 0, and that the goal is to simultaneously configure the first counter to be 3, the second counter to be 5, the third counter to be 4, and the fourth to be 7. All right? The button wiring schematics are still relevant. In this new voltage configuration mode, each button now indicates which counters it affects, where 0 means the first counter, 1 means the second, and so on. When you push a button, each listed counter is increased by 1. Okay, so we never go backwards. So a button wiring schematic like 1-3 means each time you push that button, second and fourth counters will each increase by 1. You can push each button as many times as you like. However, your finger is getting sore from all the button pushing, so you will need to determine the fewest total presses required to correctly configure each machine's voltage level counters to match the specified voltage requirements. All right, and this one is 33 for the test input. Yeah, what's the fewest button presses? Okay. So now we need to parse the voltage. Where is my parser? Right here. That's the button. There we go. So let voltage is equal to entries of entries len minus 1 dot parse unwrap. And I guess we could just make it a vec of view size like I did before. SMAP says seems simple enough. I think it does actually. Voltage. And if we create a, I can't just do it entries parse unwrap. I have to be smarter. Split on comma. Oh no. It's worse. It's 1 dot entries of entries dot len minus 1 dot len minus 1. That's terrible. I don't want to write that. Okay, let jolts is equal to entries of entries len minus 1. And then this becomes jolts of 1 dot jolts len minus 1 split on comma map num parse unwrap elect. Yes, I think so. Field voltage is never read. So let's actually print out our voltages. Make sure we got everything voltage correctly. Okay, so the first one is, where is it? Here it is. 3547, 3547, and the last one is 10, 11, 11, 5, 10, 5. Correct. Okay, good. I think we're ready then to write part 2. So part 2, well, let's write a find voltage. I think I could just do the same thing. Right, AOC lib, BFS. We have a 0, and this time we're looking for voltage levels. So we need to start at 0, and it's going to be self voltage len. That's going to be our starting state. And we have a count and voltages. I shouldn't need to specify this here, the type. That was just me messing up. And then here we don't need the count, but we do need the voltages. And we want to say voltages equal to self voltage unwrap. Vec new. All right, we'll just try to get it to compile. And we have to dereference all the time. There we go. Okay, so it compiles. Let's put it in part 2. And it's not find pattern, it's find joltage. Okay, we don't need that comma there. And option unwrap. Okay, perfect. So for this, I think it's similar. Self buttons, iter, map b, count +1, comma, joltages apply. Okay, so that's going to be a little different. Vec I32. Let's make it vec usize. Because that's what I made the joltages. So I don't have a type for joltage. So let's make a little function here. Fn push joltages is going to be a usize, and then we have a button b, not b, but button, and then we're going to return a vec of usize. And that'll be the new joltages. And it's going to be similar to the push for the lights. Let's see if we can do this. Here it is. Did I mean that to be find pattern? Oh, you're right. Thank you. And I forgot the comma there. I didn't mess up part 1, did I? No. Okay. So it's going to be similar. We're going to make a copy of the joltages. New jolts is equal to joltages to vec. Then we're going to modify them for b in button 0 if b. Oh, no. For b in button 0. Anyway, what is this? Button 0 is... Oh, it is a vector usize. I'm sorry. For some reason, I had it in my brain that the button was a usize, but I did change it to a vec. So for each button B, we're going to modify, we're going to increment, so new jolts of B plus equals 1. And then we're going to return new jolts. Make it mutable. And then this is just going to be push joltages button collect. Let's make sure we're running the test input before we do anything. I do have to put a star there. Thank you. 33. 33. Okay. Let's switch this back. It's running for a long time. Maybe this is not the right approach. Maybe what I do is, I'm going to kill it over here. Grep day 10. Oh no. Yeah, maybe this is not the right approach. Cargo run release. Yeah, it's taking a while, isn't it? Unless I did this wrong. I don't think I did. We might have to be smarter about pushing the button. I don't see how though. What do the values look like in the input? I didn't even look. I mean, they're big, but not excessively big. I guess the fact that they get wide like this means it could be a problem. Yeah, they're big enough. They're big enough to make this run for forever, right? I don't know if there's Println. Oh no, I just want to try this out. If count is greater than let's say count is equal to 100. I just want to see how far we get after 100 iterations. Joltages. Your best solution ran in 45 seconds without cheating. Oh, there's a cheating way to solve this, huh? Cargo run. Oh, wow. Let's see if we get to 10. All right, so we're getting to 10. And we're getting numbers. Oh, I keep doing that. I need a way to pop into this thing really quickly. Ooh, yeah, I don't know. I don't know what the right approach is then if this doesn't work. So if we look at these numbers, you can see that they're going to take a while to get there. After 10, they were all in the tens. But I guess 100 layers down is too big of an ask. And we're probably consuming a lot of memory, right? Building all of these entries. We know that we're always increasing. Like, for example, on this one, we can't push that button more than 11 times, whatever button that is. So is there a way to figure out, right, this is button number 1, and I can see here there's a 1. So we know we need to push that 1. There's a couple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of those buttons will, oh no, I'm looking at the wrong thing. Sorry. Here. So here, button 1 is only here. So that has to be pushed 11 times, this button. I wonder if it's possible to do a search like that, where we look for the lowest value and see if there's only one entry for that. I don't know that would help, because, well, we know we have to push this one 11 times, and then we can work on the rest of them. And here, there's only a single one that'll increment this last one. So we know this has to be pushed 116 times. Oh no, there's 2 4s. Never mind. Oh, one thing we could do is we can clamp it. We can say if we go beyond the value we need, we can chop. Yeah. So let's add that to the code, because this is obviously not going to be the solution. So we can look to see if there's no reason to push a button beyond the button that's required. The value that's required for that button. So what I can do is I can make this an option and do a filter map here. Oh, I can't. Because I'm returning the count. So I'd have to just do that here. Okay, I can do that here. Use size, comma, this. And then we'll just call push directly. push of count and joltages and B. Right, and then push will return the thing, and I'll just add count here, count usize, and then we'll just add count plus 1. So we're going to increment all the jolts. We're going to compare them to make sure if yes, new jolts, zip, self jolts, joltage. Oh, there's no self in here. Limit. It's just going to be usize. Self limit. Dot map. Dot any. AB. I don't know if the zip returns a tuple or just two things like that. It might be a tuple. And A is greater than B, then we're going to return none. Else, we're going to return count sum, count plus 1, new jolts. Unknown. So what is any? Oh, really? Self joltages. Okay. It's now very complicated, but it's working. I mean, this is the idea. So, filter map, right? There we go. And zip needs an iter. I can do that. Consider dereferencing. And now change the closure to accept a tuple. I was asking. Okay, there we go. You solved it by doing one position at a time. Oh, there you go. Yeah, that's a good idea. Let's see if this runs though. And then we can play with that. I'd like to think I would have thought of that eventually. Right, so for this one, for example, we need to push. Well, that's the thing. I mean, each one of these buttons can be pushed 136 times, right? There's 4 buttons, but then you can push any combination of those 136 times. Okay. So this doesn't trim it very much, unfortunately. All right, so finding this, we probably want to search, we probably want to find the fewest button pushes. So we look at the lowest number. Can we do that? So here, it looks like 31, for example. So we get button pushes that get us to 31 on that. But that's going to include the solution somehow, right? Because if we find every button push where that number hits 31, oh, I guess what we could. I might have to bail on this one. Unfortunately, this is not something that my brain is. If we look at each of the buttons and push each button until we get to the 31 for the first one. Ma'am says, okay, turns out to not be in my wheelhouse. I wonder if, I'm trying to think if it was similar to a puzzle we've already solved before. And I'm struggling to think of something similar. And because that usually is what I use to determine the approach here. There was one. Oh. Yeah, one of the things I probably should do is learn how to use those polynomial solvers. Though I don't like, I prefer to write all the code myself to solve these things. Let's, yeah, this is not gonna finish, right? Ever. And it's probably chewing up all my memory. Let's see if I can find just the smallest, the fewest button presses. I had to use a solver library, not something I would ever need to write, so I take that as a library and allowed to use for this. Okay. All right. Let me see if I can find, at least have the solution of the smallest joltage, right? So I can say let smallest is equal to self joltage iter min unwrap. There's going to be a min in there somewhere. And then the finishing state will be if we match that. Oh, I do need to get the index of it. And it's a.1.compare with b.1. Right? And there we go. And I don't think I need that anymore. Maybe? usize and usize. Okay. So now we want to say if joltages of idx is equal to smallest. And then I'd want to print it out. If, then println count joltages. I just want to see what it turned out to be. Wow. Okay, even doing the smallest. It's easy to get the test to pass. And some of the machines other requires too much processing using pruned searches. Yeah. Let's switch it over to the test so I can at least see those. So what I'm trying to do is look for the smallest one. Oh, it only finds the first smallest one. Right, we need to find them all. The BFS isn't helping us. Because BFS stops as soon as it finds the first one. It doesn't keep going. 0, comma, vec bang. 0 usize, self, joltage, len. Visit is equal to true. Hash set new. Okay, and while let sum count jolts is equal to q pop front. So if I want to print them all out. I'm running the test input now, so that's fine. If joltages idx is equal to the smallest, jolts is equal to the smallest, and we found one way to get to that smallest value. The only thing is there's multiple ways, but this is the first way to get there. So println this, I guess, jolts like this. Else, we're going to continue looking to see if there's other patterns. So else if visited insert jolts clone. Yeah. Then we're going to say for I guess self. Yeah. For button in self buttons. If let some new state is equal to push count self jolts and button, then Q push back new state. Let's see if that works. And we're going to comment this out and return 0. Because why not? Clone needs this. Count is already that. Jolts needs a reference. Okay. Cargo run. Yes, I would love your ideas, TV Josh. So this is okay. So we do eventually run out. So we have a bunch of ways of getting the smallest one to be 3, I guess. Is that what the smallest one is? This we can close up. Yes, 3, 5, 4, 7. So we found all the ways you can get to 3. Am I using linear algebra? I am not. I don't know how to do that yet. I haven't learned that. People talk about polynomial solvers, and that's certainly one way to do it. I don't know if Rust probably has a library for it. Let me just see. Println finding IDX smallest. Index 0, we're finding 3. Index 4, we're finding a 2. And index 3, we're finding a 5. So I guess you could consider all of these the starting points. If we have all of these could be the starting point for the next smallest. Right? But we would have to not push any of the buttons that would trigger that one. It'll get a little more complicated, but I think we can. Let mut tried is equal to hash set new, while tried len is less than self joltages len. We find the smallest one. Filter jolt not tried contains jolt. We have to make sure we enumerate it before we filter it. And then this will give us our new smallest. We then find that, except we want to start with our previous jolt values, not 0 usize. So, right, and this is going to generate all of these things, and then we're going to have to feed those into the next vecdeck. All right, let's see if we can do that. Let mut starting. Oh, we have to do it here. Starting state is going to be vec bang 0 usize self joltage len. Okay, and then we're going to create a next state. Build it back new. And we're going to Oh, this is going to be a vec of this. Each one of the possible joltages. Okay, let's try that. Can I do this? I don't know if it'll let me do that, because then it'll just be a slice of 1, and I want that to be a vec. Let's try it this way. Vec dec of usize vec vec usize. Can I do that? Pooh Banana, good luck. See you later. Thank you. I will. I'll endeavor to get this done. So this is actually going to be our starting stage. So let's put it up at the top. And I'm going to reset that. And our next stage is going to be this. We find the smallest. We reset this thing here. We don't need that. We don't print out jolts. What we'll do is say next stage, push jolts clone. Okay, then we loop over all, finding every possible answer for that stage. But we have to make sure that when we go through the buttons, we filter out any button for a stage we've visited already. But is that even going to work? Okay, let's do it in our head. This first one, we can push this up to 3 times. This button. No. This button or this button. Any combination of these 2 buttons, we could push up to 3 times to get that. And the other buttons could be pushed whatever. And in fact, they are. We do need to keep track of how many times we're pushed a button, and that's not even in here. I'm just trying to find a solution at this point. How many is that? That's a lot. Okay. So what I'm thinking here is we would just do starting stage equals next stage. All right. And then we do want to check to see if we found the answer. Each one of these has to have the count. It's not as simple. Okay. I guess it's this then. 0, comma, that. And then this just becomes starting stage, right? Is that going to work? Let's see if it even compiled. I don't want to run it. Yeah, I'm not running it. Okay, good. I can't do this. Bacon Clippy. Expected vec usize, vec usize. Oh, no, I want a vec of these things here. I'm getting lost in the parentheses. So I guess what I can do, yeah, each one of these can do this, right? And this can push the count plus 1. Oh, just count jolts clone. Like that. And then give tried and I haven't, yeah, I got to insert tried here. So tried, insert, we don't care about the jolt, we care about the index. like that. I need colored parentheses. Yeah, I've seen those. I've seen those. I want to know what starting stage looks like after everything's done. Let's just say println working on IDX. I have no idea if this is actually going to solve the problem. I'm just curious as to how far it's going to get. It does eventually come up with a final set of stages, and they're all the right answers, right? 3, 5, 4, 7, 7, 5, 12, 7, 2, and 10, 11, 11, 5, 10, 5. So it eventually finds them. And all we care about is this final count here, or the shortest one. There's something better than colored parentheses? Is it a programming language that doesn't use parentheses at all? So I wonder, can we do this? Is this going to work? Println, oh no, return. We're returning this value here, right? I have 0 down here. Let's get rid of the BFS. We know BFS isn't going to work. There's no reason to keep it. So I can say starting stage, iter, map, s, c, for count, min, unwrap. Consider dereferencing the borrow. 33, but we know DFS also worked on the first thing, so I'm not holding out any hope. I'm going to get rid of the print statements here, and we'll give it a shot. What's the worst that could happen? Maybe if I can print them out as I'm solving them, maybe it'll show me I'm making progress. Self. Let's just print out the self joltage. I don't know if it's working. Yeah, even the first one is taking forever. Well, it was an interesting approach. What's the first one look like? Not that. Input 2025 10. 90, 46, 86, 53, 31. Maybe it's time to start doing those working on. Just to see if we're making any progress at all. So it's working on the 31. It's trying to get to 31. And it's not even getting there. Oh, you know what we could do is we could filter out buttons that affect that particular thing. Right? We could say self buttons, iter, filter, B contains IDX. That's another optimization. We can't do contains. ID find. What's B? B is a button. Oh, B.0. Contains. There you go. Doesn't like it. Now it likes it. You wrote VS Code plugin that draws match parentheses within a closed shape with very little visual noise. Ignore the icons. Okay. Oh, I see. That's pretty wild. That's pretty wild. I'm not sure I like it. Let's close up some of these things here. That was from yesterday. That's the infallible that we looked at before. Okay. So can we filter those out? Well, oh, look at that. It found 2 right away. Now it's working on 46. Oh, right. And we want to filter out any button. So it's making forward progress. Look at that. It's working on 3 now. What else can we filter out? We want to filter out any button. Oh, we do have this tried. So we want to only use buttons, and we don't need to filter it each time. Right? There's no reason to do that. We're on a particular set of buttons. So do we only want to look for buttons that don't include this button? Right? So let usable buttons is equal to self buttons. Iter map B. And this is going to be a button, which is going to be a list of vectors. And we want to make sure that none are in this. Oh, we want to wait on that then, right? We want to filter. So now we want to say tried iter. No, tried B iter. B0 iter. Any button tried contains button. And we want to not that. Println usable is usable buttons. Let's see if I got that right. Uh-oh. I should kill it right away if it doesn't. Oh, look at that. So usable buttons are, oh, this is a filter. I didn't collect into a list of all the buttons here. So for this one, for the first one, it can use any of the buttons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 buttons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For the next one, it's only, we worked on 4. So any button that has a 4 in it cannot be used. And that's true for this one. So button in usable buttons. That might speed things up. I'm going to take this out because it's very noisy. Now it's going slower. Oh, no, we only want to use the buttons that actually match. Any button right, so it doesn't contain anything we've already tried, but it only contains filter B, B.0 contains IDX. Right, so we only use the buttons that exist and remove any buttons that we've already pushed. Let's see if that works any better. Not much. I am going to print them out now. Println buttons, usable buttons. Let me impl display for button just so I can read things a little bit more. Here it is. I guess what I could just do is use the interior thing, right? Like this. And that'll just write it out as a vector. I'll put a B in there just to make it. Oh, right, because I'm not printing it out that way. I'm still printing out as debug. Yeah, I don't think this is going to work either, right? Because oh no, it's getting there. It's going to take forever to run though. I just want to take a look. So 21,000 possibilities for the first one. Can we just, instead of pushing it once at a time, we should just be able to push it n times and get it? Yeah, 7 million possibilities. Okay. That's why it's taking forever. Yeah, I think we can, instead of pushing it once, we should be able to push each button. Like this one I can push 31 times in a row. I don't need to push it once and then come back to it. So we should be able to look at which button we're pushing, see how many times left to push it is. You see NVIM, you follow? Yeah. There was somebody earlier asking why do we use NVIM in this big year of 2025? And either I'm stuck in the past or I'm embracing the future. Take your pick. So let's say next stage push count jolts clone. No, for this push here, what we want to do is say how many times do we want to push it. Right? So we're going to update this to say we're going to push it this many times. And is there any reason to do that? Put the count in here. I don't think so. We don't need to do that anymore. We can just say count +1, new state. That gets rid of that. There. Okay. But I should be able to say push it how many times. So we know the current value. We're working on index. Let val is equal to jolts of index. And we know the value we're trying to get to, self-joltage of index minus jolts of index. So we can push it that many times. Val. And val is the wrong number, this wrong variable name. pushes. All right, so now we'll add pushes here, which is a shame because now it's going to stretch it out again. Instead of saying increment by 1, we're going to increment by pushes. All right, is that any better? No. So it couldn't even find a solution for that. Let's see if let's use the test code to see why it's not working. Part 2 is 10. Now it's supposed to be 33. So I broke something. Working on 0, which means we can push these things. We found 2 possibilities. Actually, this should be count plus pushes here. That's probably why it was 10, right? 33. There you go. Okay, so it's able to find the answers using this logic. Super 57 working on this. If I just do this. Oh, it's an array though. Okay, let's get rid of that code. So those are the buttons we're trying to push. We found 2 possibilities. Then we work on button 2 and we found 4 possibilities. We work through this button here and push this button here. And then we found our answer somehow. 3 possibilities. And we came up with one of them. Let's and we know, so we can say assert EQ. Oh, yeah, we have to assert that they're all equal to the final answer. So let's take a look at just the first entry of, oops, now we have a warning. I'm not using FMT. That's true. Okay, let's, just the first one. First.text. So this will be head-1 of input 2025 10 text into first.text. Right, so that's just that one. So if I just run the first one, cargo run, we found 4 possibilities to get to 31 here. So maybe this is not for S in next stage, println S. And we found 7 ways of getting to this stage, but now there's no buttons left to work on. We should, yeah, we should abort if we don't find anything, right? If, so assert next stage len is greater than 0. That way we'll stop right away. We won't keep trying to. All right, and if I change this back to 1, I mean, it makes sense that you would have to. But see, this has a whole bunch of different other possibilities. And found 21,000 possibilities. It's interesting, though, that it did work for the test input. Yeah, it's almost 9 o'clock. I have to call it, unfortunately. Maybe I can finish this tomorrow. After I've thought about it a little bit more. There we go. Now, for day 10, here's what I'm thinking. How far did I get? I hacked a little bit after the stream yesterday just to figure out what was going on. Let me see. Cargo run release 10. Yeah. So it's not, it's, you know, after the first button, it's finding 21,000 possibilities. Oh, the other thing I wanted to do, I think one of the things that could speed things up is for next stage, I'm using a vector. But if I use a hash set, that should reduce all the duplicates. And starting stage. Where do we use that? This is a vec. I guess I could just pull it out as a vec. Iter map, I guess collect into a vec. Well, let me do that, or do I have to do a copied? I don't want to run. I want Clippy over here. Vec, expected vec usize found. Yeah, reference. So we have to copied or cloned. Okay, so now if I run, yeah, it definitely reduced the number of possibilities. So from 21,000 to 6,000. Took you a while to work out what was needed. Okay, but you got there in the end. That's the important thing. So here's what I'm thinking for this. Oops, in the wrong window. If we have, let's say, I'm going to, oh, it's still a lot for this second one. This went from 7 million down to 7.5 million down to 2.5 million. No, I'm flipping back to day 10. I just finished 11. So let's go here back to day 10. Let's just grab this one line here, just to pick an example of what I'm thinking of. So we have this. This is our input. These are the numbers we're trying to get to, and these are the buttons that we can push. So if I label this as A and B and C and D and E, we have these 5 buttons. So if I say this is A, B, C, D, E, and button A can push 0. So we know that we're trying to get 7 in the 0th joltage device or whatever it is. We know A can do it, B cannot, C can, D can, and E cannot. And we know that that has to be 7. So some combination of A plus C plus D needs to be 7. A does not have 1, and neither does B, neither does C. D has 1, and E has 1, and somehow that has to be 5. Let me just do all of them. Let's see, 2. This has 2, this does not have 2, that does have 2, and that does have 2, and that has to be 12. This has 3, this has 3, this does not, and this does, and that's 7. And then 4s. There is a 4 there, no 4, yes 4, no 4, yes 4, and that's 2. So here's where here's my starting point. And I'm looking at this and I'm saying, well, you know, what we can do is we can treat this like equations, right? We have A times 1 plus B times 1 plus C times 0 plus D times 1 plus E times 1 is equal to 12. We can actually reduce this by looking at, like, so if we number these rows here, we number this 1, 2, 3, 4, and 5. Actually, I should number it by the buttons, right? 0, 1, 2, 3, and 4. So we can see that we can subtract row 2 from row 1 and get a new matrix. If we subtract row 1 from row 2, we would end up with a 0 here, a 0 here, and a 7 here. And that would be our new system of equations. And then we can subtract 2 from 3 and get yet another thing. Let me actually document what I'm doing here. Subtract row 2 from row 3. And then what we do here, we can do it again. At the new row 3 here. Oh, what did I do? I know I meant to do this one. Subtract row 1 from row 2. And now we can subtract row 2 from row 3. And that'll make this 0, right? So we'll have right? And then we're left with, and then we can eliminate that row because why? This is, what is this? Subtract 2 from 3. Oh, did I? Okay. There. And then eliminate row 3 because 0. 3 is 0. So remove it. And then we're just left with these two that you can't subtract one from the other. And then use this information somehow to figure out the different ways you can get the 7 and 2 to work. And then once you have those, go back to the beginning, fill in the numbers, and figure it out from there. Let me just make sure I got this right. 0, 2, 3, 4. We got 2 and 3 here, 0 and 4 here, 0 and 2, and 1, 2, 3, 4. Yeah. Is there a better way to do it, though? Right. So now we can use our existing solver because now we have much fewer states, many fewer states to use. So use existing solver. Find the various solutions because there's going to be more than one solution. Right? We can push this button 2 times. Oh, look at that. Wait a minute. We push this twice. Anyway, so this is the approach I'm trying to take, but it looks like there's no solution for this. I can't see how you can get there, because every button you push has both, will activate both. Oh no, if you push D 7 times and E once, that'll work. Oh, except we know that we can't push E at all. Okay. That means we can eliminate that and clear that button. Those buttons. So any button referenced here can't be pushed. So that means actually we can go one more step, right? We can actually say subtract 4 from 0, and we get just row 0, and this goes to 0, and this goes to 0, and this goes to 5. Okay. So now we have one solution with 5 button presses. So if we have a struct that says, solved presses 5, and the button is going to be an array of 0, 0, 0, 5, 0, because there's only one we'll call it solution. Right, we'll do this in Rust format. So you can then take this and go back into the original matrix that you had. Stop me if I'm not making any sense. But we can go back to the original matrix, apply to original matrix. So if we grab this, and we know we're going to push D 5 times. So we can eliminate the D's, and any one that had a D gets reduced by 5. And now we have a more solved matrix, right? And then we can start over again from the beginning. Spoof, hello. And then we can start over from the beginning and keep trying to solve it. I finished day 11, and I'm back on part 2 of day 10 because I'm trying to talk my way through it. I have about 30 minutes left before I have to go. So I wanted to see if I could figure out a way to generate, at least get myself part of the way there. And now we can do the same kind of elimination thing. We know that 1 is 0. Row 1 is 0. So remove it and clear those buttons. So this becomes this, and then we say nothing here and nothing here and nothing here. And now we have, oh, look at that. No spoilers. Have you started 11, Spoof? I'm going to kill this because this is insane. 10 part 2 kind of cheated by just pulling in a library. A lot of people have done that. I saw people talking about using Z3 to solve it, but I don't want to do that because I'm stubborn. I've read the statement for part 1. Okay. Yeah. I mean, I went a little overboard with my part 1 solution because I was anticipating part 2 to be different to what it was, but I got there at the end, so that's fine. And now what we can see here is these are both the same. I mean, there's 2 pairs of the same thing. So now there's no more reductions we can do, but we can use the solver, right? Use existing solver to find solutions for this state. And because this is smaller, actually we can probably reduce it. Right? We can remove the duplicates. And then we can use existing solver. Okay, so what are the solutions here? We have a solution. If we press we can't press A. Well, we can press A twice. And then B 5 times. So that would be 7 presses with buttons A twice and B 5 times, 0, 0, 0. That's one solution. Another solution would be pressing A once. I think it's still 7 presses, right? A once. B 6 times. And then C once. That's 8 presses. So obviously that's worse. And then solution, we could press, I'm not sure yet. We could press B 7 times and C twice. And that's obviously even worser. That's 9 presses. And then there's a bunch of other solutions, right? So then what we do is we take the best one, smallest, because you could have multiple solutions that come up with the smallest value. You want to try them all and apply it to the original matrix. So that's this matrix up here. Let's assume that we choose this one. My runtime for day 10 part 2 is a few hours. The code is super ugly, so I guess I'm stubborn too. Yeah. Yeah. I just wanted to say, everybody, Codes, thank you for not doing one of those this year. Yeah. Because these are painful. But this is the reason I'm going through this now, is to try to see if I can add to my library a little general purpose solver. So it's not a full-blown Z3 thing, but at least something that'll work for these kind of puzzles. Right? You're not going to do this ever. Okay, fair enough. But somebody was saying in chat that Eric had a way to solve it without using Z3 and without using Gaussian elimination, somebody said? Used an ILP, yeah. People have said using that. Yeah, black box, which solves the problem for you, right? All right, so that means that if we take that first one and we apply it to this matrix, that means we've used up all of our A's and used up all of our B's. No, I shouldn't do it that quickly, right? So we pushed A twice, which means we can subtract 2 from that. 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 And then we used B 5 times, so we can subtract 5 from that and subtract 5 from that. And now, because all of these are zeros, we have solved, quote unquote, the problem. Map says, I've decided I've been coding for 45 plus years. Wow, nice. And never needed one of these solvers before, except for AOC. Don't intend to start writing my own now when a perfectly good library exists. That's also a fair approach. So we've used the 5 here, and we've used the 7 here, which means the answer So 5 from original solution plus the 7 from this most recent solution equals 12, which is the answer. I think is the answer for the second one. Let's see. 12. So if I can do this by hand, I should be able to teach a computer how to do it. This is my hypothesis, is that doing this by hand means I can do it by computer. If I can write code that'll do this for me, that could be fun. If I was still coding for work and this is a regular need, it would be different. Yeah, but for work, there's an argument to be made that you save time by using a library. And then the counter argument to that is if you're using a third-party library, you're dependent on that being A, maintained, B, bug-free, and C, not malicious. So it's better to roll your own. People will push back on that, saying that's, the not invented here syndrome. But for critical infrastructure, you need to roll your own. You would have to understand the library better as well. Yeah. Okay, so I'm going to commit this also as my changes for day 10, even though it's just a giant comment explaining my thought process. And then what I'm going to do, I don't know how 12 is going to go tomorrow, but there should only be one part for 12 if he follows his normal puzzle generation process. That the final day only has one puzzle. You saw super quick solutions without the use of the libraries, but your mind cracks when you're looking at linear algebra stuff for too long. Yeah, I mean, this is why I'm writing it down, because I will forget all of this. It's not Christmas Day, so it might be different, yes. Or Christmas Eve, right? Oh, no, that's right. They were 25, so Christmas Day. You're right. Okay, so I'm going to save this. All I did was add this giant comment at the end. Git commit -am giant comment describing my attempt at a solver. Git push. And I am going to just call it a stream at this point here. The solution for day 10, which is, let's go here. What I was trying to do originally was saying, well, we could use this Gaussian elimination, and I was trying to work my way through it, and I did this all on stream, so I'm sure I bored a lot of people about how we could collapse the equations down and then reinsert the values and blah, blah, blah. But there's a simpler way to do it, is if you think of, and this is what I'm going to try to do, and hopefully we'll come up with something, some implementation of it that works, is if you have a button, or a set of joltages that are like 8, 12, let's just pick 3 and 18, for example. To get to 8, 12, and 18, you do have to pass through 4, 6, and 9. And if you can get to 4, 6, and 9 from 0, 0, 0, you know how many button presses that is. And you just multiply by 2, and you get 8, 12, and 18. That's the idea. So the objective is to try to come up with a set of button pushes that makes all the numbers even, then divide all the numbers by 2 and come up with a solution for this level, and then just multiply that by 2 to get there. and then add the original button presses. So for example, if you have 9, 12, and 18, it takes one button press to get to 8, 12, and 18. And then it takes n presses, then divide by 2 to get 4, 6, and 9. And then you have n presses, so you get 2, 4, 6, 9. And then multiply by 2. I don't know if I'm describing it well. I'm not, I didn't create a PowerPoint for this. But this is the idea. And so I want to see if I can implement this idea. So you multiply the n by 2, you add the original 1, and then you get it. But you can also apply the same logic to this, right? If you have 4, 6, and 9, it'll take a press to get to 4, 6, and 8, and then you can get to 2, 3, and 4, right? And then you take 2, 3, and 4 and make it 2, 2, 4, and then you get 1, 1, and 2, and then so on until you get to 0, 0, 0. That's the idea. So let's see if we can make it work. First thing I want to do is I want to come up with all of the combinations of the buttons we can push. Vec use size. Right, if there are 3 different buttons we could push, then there's 2 to the 3 different combinations. Right, and we're not using it yet. So we need to generate all the combinations. And the easiest way to do that is just with a bit mask. So let's do that. Let num combos is equal to, and it is the number of buttons, 2 to the power. I think 2.pow works. Buttons len plus 1. Right, so if we have 3 buttons, oh, maybe it's just buttons len. Yeah. Let's find out. Oh, must specify concrete type. It's suggesting U32, I32. Let's just use usize since everything else is usize. Consider giving a buttons an explicit type, but you should know the type from here. That's interesting. If I use the length of it, it needs to know the type before it can infer this value here. That's unfortunate. Sure. Okay. So let's see if we can do, you know what I'm going to do is I'm going to switch over to the test input so we can actually take a look at this. Oh, I have it set to first. Interesting. Ah. How many buttons is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 buttons. That's going to be a lot of combinations. Let's take a look at the test. Yeah. Okay. Let's use the test input. And I can print out the buttons as we go through them. Where's the combinations? Here we go. So we're going to say for bitmask in 0.num combos. I guess I didn't need to pre-calculate it. I can just grab it here. Oops. Come on. Like that. And now we can look to see which buttons we want to insert into this latest combo. So let mut combo equals vec new. And each button I believe is just, yeah. Okay, it's a vec of buttons. Okay, it's a vec of view size. So you can say for button in zero dot dot buttons len again. Then we can say if bit, button shifted by, no, one shifted by button and bit mask is equal to 0, then continue. Otherwise, we're going to insert it into our combo. McNuts, hello. And the combo is going to be a vec bang of 0 sizes of the length of the joltages. Self joltage len. Like that. Raymarch, hello. Oh, we're not on the self yet. Oh, and now we need this. Okay. How does it not know? I don't understand why it gets it wrong. It's a vec of view size. Why it can't infer it? Just because I grabbed the length earlier than the thing. Anyway, so now we're going to say for each button entry, be in button 0. Right? Ooh, isn't this a? Oh, it is. Oh, right. Buttons of button 0. Now it's a U size. And then we're going to say combo B plus equals 1. And then after we're done with that, we're going to say combinations push combo. So those should be all the combinations. Obviously, we have an issue, or Clippy has an issue with this. For button item and buttons iter enumerate. That sounds better. How about index button in buttons iter enumerate? Now this is the index. And then we could just say button 0 here. Oh, I didn't want to consume it. Okay, we're getting there. So now let's print out all of the combinations for C in combinations. Println. You know what I could do is I could show the bit mask that I'm messing around with. IDX C. And there goes the train. Iter. Sorry about that. Enumerate. I'm imagining you can hear the train there. So let's say 8:B, IDX:8B, and then C. Writing against part 2. I'm trying to. Hopefully I'm going to succeed. We'll see. Oh, right. I need to switch this down to day 10. So in order to do that, I'm going to flip these around temporarily. Okay, so I think this is where, let's take a look at this last one, because this might be the easiest one to understand. So if where the bit mask is 0, we have all zeros. You gave up? I think I have an approach that I talked over with a friend. It took us a while to come up with it. But it makes sense based on previous types of puzzles like this, where what we're going to try to do is just figure out a button sequence and then double it. And then add that to another button sequence. Well, I explained it at the beginning of the stream, and now I can't explain it for some reason. But let's see. If we have buttons 1, 0, 0, and double it and give it to the next person. That's a good idea. So if we have buttons, this is button 0, 1, 2. So we're looking at button 2 is 0, 1, 2, 4, 5. 0, I don't know what order this is. 0, 1, 2, 4, 5. Yeah. Okay, I think this is right. If we have buttons, the first three buttons, we have 2 zeros. Oh, 3 zeros. Then we have 2 ones. I see 2 twos, 2 threes. Yes. 3 fours and 1 5. Okay, so I think this is working. So if we have all these combinations now, I'm going to blow away this old fine joltage. The whole thing goes because it wasn't working. Wow, I did a lot. Boom, gone. Oh, I have to do those as lines as well. Okay. The encrypted duck puzzle. What was the encrypted duck puzzle? I remember doing a puzzle in Everybody Codes in which we had to multiply using repeated addition. Which puzzle number was that? Any recommendations for a beginner learning Rust? Have you gone through the Rust book yet? If you haven't, I would recommend starting with that. And then I would recommend, whenever people ask me this question, go through Advent of Code. The first 2 or 3 days generally are puzzles that are simple enough that you can get your feet wet, as the saying goes, with Rust before overcomplicating things. 2024 question 19. Okay, let's take a quick peek at 2024 question 19. Oh, this is the AOC leaderboard. I'm not going to look at it because I'm very embarrassed by my performance. Oh, I'm logged out. Okay, that's all right. I can still look at it, right? Yeah, it's similar to this where we had to do all the rotations. And you have to figure out the rotation of the thing. And in order to do part 3, yes, you had to figure out how to multiply the rotations together. Yes. Rustlings is also very good. I went through that on my stream and I posted those solutions to YouTube, although I haven't done it in a while. And I imagine that it's more... I imagine it's different now than it was. But yeah, this is the idea, is what we do is we figure out how to multiply these things together. Actually, I'm going to do division, but it's the same idea. So in order to do this, guess what we could do is just write a helper function. Self search for vecbang. Oh no, not vecbang, self joltage. And that's what we need to start off with. And then search is going to be recursive search function, fn, or maybe we should call it count presses. Count presses. And we have a goal for what presses we're looking for, and it's going to return a usize. Okay. What we're going to do is go through each one of the combos and subtract it from the goal. And if they're all even, then we can use that as our solution by dividing by 2. So we're going to try that. For C in self combinations. Oh, I forgot the self. Next goal is equal to goal zip C. A goal iter, right? Goal iter zip C. And now we should be able to map. Does this give me a tuple? Let me just do this just to see what it is. It is a tuple. Okay, so we're going to have our goal value and our combo value, G and C. And what we'll do is we'll subtract G minus C. Oh, you know what we need to be able to verify though? Collect. Vec. I missed something up here. Oh. Why is this bad? Am I losing my mind here on the collect syntax? Yeah, collect colon vec. Is this the default color theme for NeoVim? No, this is something I'm using for streaming because it has a high contrast. This is not my normal color scheme. My normal color scheme is Habermax, and this is Murphy with a modified background to be black. You've implemented for this AOC data based on a tutorial on Reddit. Okay. I won't suffer for too long. Hopefully not. Although I am having a problem with my syntax here. If I just do this, that likes that. So if I say dot collect vec, oh, I forgot the I put the opening angle bracket in the wrong spot. That's what I did. But I can't do this directly. Oh yeah. I can't do this directly because if G is greater than, no, sorry, if C is greater than G, we don't want to do that. I guess first thing we want to do is check to see if the goal, if goal iter all G is equal to 0, then return 0. There's no, then we're done. There's no more button presses to do. So that's the first thing to check. I guess the next thing to check to see is, while we're looping through here, if goal iter zip C, this is bad because now I'm going to do the zip multiple times. GC, if G is less than C, nope, this should be any. Then we want to continue. All right, if we can't subtract C from G, then we can't use this button push. So then we create this new goal. And then we can check, say if goal, sorry, next goal, iter all G, G is multiple of 2. Then we want to call count presses and multiply by 2. Plus, oh, you know what we didn't do? We don't know how many button pushes are in that combination. So that's something we need to change. We need to make this a vec of usize, comma, vec usize. Presses, oops. Presses, comma, vec of amounts. So the first parameter here is how many presses it takes to get these values. And the second is the values themselves. That means we need to change this combo thing to be, I guess we can count. If I can spell it correctly, and then say presses plus equals 1. Presses. You know, there also is a count ones. I could just say bit mask count ones. And that would tell me how many things we're pressing. So let's do that. That might be, oops, I messed this up here. Yeah, okay. And then this is a mismatched type because, oh, because I did usize, and I bet you count ones is not. Yeah, it's U32. Okay. Oh, So we have to say underscore C here. Oh, wait. But goal is a U. Oh, okay, okay. Let's do this then. Presses, combos. That way I can put this directly in here without having to worry about it. Took me a while to read that error message. All right, we're not using presses, but now we're going to say we want to calculate let total is equal to presses plus 2 times self count presses. That music, White Christmas by Danny Evo, it has this abrupt end right there, but then it keeps going. It's weird. Have I checked out the Helix editor yet? I played with it a while ago, several years ago when it first came out. My brain, I'm an old dog and I can't really learn new tricks, so it was difficult for me to use it. And I know that if I just kept using it, I'd eventually figure it out and it would click. But I'm so used to NeoVim. There's also Zed, right? I've tried Zed as well. And, you know, it's another nice modern editor. I just haven't made the switch. All right, so we're going to count presses on next goal. And now we want to save the minimum. Okay, let's do that. Let's create a minimum here. This is going to be a U size, an option U size. And then we can say if minimum is none, or is there a way we could do this cleanly? Like, can I just say minimum if let sum min equals minimum, or minimum is none? Will Rust let me do that? If min of total is less than min, then minimum, I won't let me do this part. There's a replace or something like that. Yeah, replace total. I don't think you can do this because it's going to be broken. You're using Astro NVim. Okay. Did I try out Mug? It's in alpha and being written in Rust, aiming to improve Git. Interesting. I'll take a look at that after the stream. But alpha is not something that I can use right now, obviously. Okay, so yeah, you can't do an or. Can you do it the other way around? Minimum is none, or? No. I wish there were some simple way to do this, because I want to do a minimum replace. If minimum is none, or sum total is less than minimum. Can you do that? Oh, it lets you do that. All right, let's go with that. And then this becomes the minimum. And that way we can return an option U size here. And down here we have to do an unwrap. Like the good Cloudflare programmer that I am. Will this build? I want to make sure I'm on Clippy here because I don't want to run it. Expected option U size. Oh, I have to say option sum 0 here. Okay, that's the first error. And oh, right. And I have a, if let sum answer is equal to self count presses of next goal. You have to do it this way. Then we want to say it's 2 times the answer, like this. Okay, we're getting closer. We're not using hash set or vecdec anymore, because I guess I was using that for my previous solution. And then this if statement can be collapsed. Oh, I guess, yeah, I could just put and. Okay, and this doesn't like something here that I messed up my... Oh, because I collapsed one, I have to remove one. Yeah. All right, it compiles. It would be amazing if it just worked right off the bat. I do have it set up for the test input. So I'm going to go over here and cargo run. And main has overflowed its stack. Oh, because I didn't subtract, did I? No, I did. I did subtract. That's what this is. And we do hit 0 here. So let's print this out, what our goal is. I wish Rust had, the equivalent of Python's equal like that. That would be nice. It has DBG, but DBG's output is very noisy, so I don't use it. Let's see what this comes up with. Oh, right. I forgot to divide by 2. If it's a multiple of 2, then we need to divide everything by 2. Let next goal is equal to next goal iter map ng over 2 collect. And if I just pass it in like this, it might figure it out. The size for the value is what? Try explicitly, even though I'm passing it in here to count presses where it's expecting I guess it's not really expecting a vec, right? It's expecting a slice. Okay. 33. Was that the right answer for part? Oh, that's day 11. Let's go back to day 10. Yes, 33. So it comes up with the same answer. Let's get rid of this, because it's very noisy. Bake and run. All right. And now I'm going to dare to use the real input. Uh-oh. That's not a good sign. That's never a good sign when it takes forever. Maybe if I run it in release mode. Let me just go over here and kill it. I don't know. Sometimes bacon kills it and sometimes it doesn't. No, it was killed. Okay, let me try running it in release mode. Okay, so it came up with an answer. Let's see if it's the right answer. Hey, that's the right answer. Okay, so that was the trick, and it's similar, like Everybody Codes was saying earlier on stream. It's similar to the puzzles where you have to divide and conquer, and you have to. We figured out, yeah, it was day 19, was it, of 2024? Smab gives me 2 stars. Yay! It took over a second to run though, so it's a very slow puzzle. I imagine other people have gotten that much faster. There's probably a more efficient way to do this. But I mean, this is the idea, is that you solve for half the puzzle and then just multiply by 2. to get to where you need to be. Right, and I have a little comment in here describing it as I was talking on stream.